You ordered a $4 plastic screen protector at 9 p.m. By 7 a.m., it is resting on your doorstep. The industry calls this overnight shipping. From an engineering perspective, however, this is not a logistics miracle. It is a systematic exercise in industrial insanity. We have synchronized commercial flight paths, mobilized regional distribution fleets, and disrupted the circadian rhythms of thousands of night shift workers, all to ensure that a microscopic piece of molded polymer arrives 6 hours faster than a standard ground truck would have carried it. We essentially constructed a hyper-efficient, machine gun-paced supply network, just so you wouldn't have to wait until lunch to open a commodity you probably didn't need in the first place. Today, we are not detailing how this machine functions. We are performing a forensic autopsy on exactly why it fractures. To understand why this system breaks under pressure, we have to look at the money behind it. The math of next-day delivery rarely works if you look at a single package in isolation. When you spend $4 on a plastic screen protector, that individual payment by itself frequently fails to cover the actual cost of moving it across the country. To keep from losing money on the transaction, the system relies on structural cross-subsidization. Your $4 gets mixed into a giant corporate pool. The company makes up for the thin shipping margins by charging users monthly subscription fees, selling digital advertisements, and taking a cut from third-party marketplace sellers. This brings us to the core economic reality of the modern shipping network. It doesn't make its profit off your single order. It only functions because 400,000 people are buying small things at the exact same hour. We built a multi-billion-dollar network of airplanes, trucks, and software just so you can get a cheap piece of plastic delivered before noon, completely subsidized by the rest of the business ecosystem. To keep costs down to pennies per package, the infrastructure requires high utilization. A robotic warehouse costs the exact same amount of money to light and heat and also maintain, whether it handles 10 boxes or 10,000. The cost per package only drops when the physical facility is constantly filled with volume. This sets a dangerous trap. While a giant shipping company can technically scale down by parking planes or changing worker schedules, doing so inflicts massive capital inefficiencies. The whole setup is built for high continuous volume. The moment consumer demand drops or a single sorting hub experiences a technical bottleneck, the math faces immediate strain. The system cannot easily downshift without losing millions of dollars in efficiency. It is forced to keep rushing forward, which means there is no safety net left when something finally goes wrong. To understand how a physical failure rips through this economic framework, we have to look inside the primary engine of the network, the regional sorting hub. This facility is not a warehouse. It does not store inventory. It is a high-velocity fluid dynamics machine where the fluid is cardboard. When a haulage truck docks at 1 a.m., thousands of mixed packages are dumped onto a primary intake conveyor. From this moment, the human element is almost entirely eliminated. The boxes enter a multi-tier labyrinth of automated steel conveyors operating at a mechanical tempo that leaves no margin for physical deviation. The core of this machine is the crossbelt sorter, a track of motorized mini-conveyor cells moving at up to 3 meters per second. To route a package correctly, the system relies on an array of high-speed overhead optical cameras known as the scan tunnel. As a box passes through at high velocity, these sensors must instantly locate, read, and process a two-dimensional barcode, executing a routing decision in less than 50 milliseconds. This process repeats continuously, tens of thousands of times every hour, running an unrelenting stream of data under the lenses. If the data matches, a precise signal activates a small motor beneath that specific conveyor cell, tilting the belt and sliding the package down a designated chute toward an outbound delivery vehicle. But this entire mechanical network relies on a terrifyingly fragile assumption, the absolute perfection of physical data. The machine does not possess spatial awareness. It cannot think, adapt, or troubleshoot. It only reacts to the reflection of light off a printed label. Because the throughput demands are so severe, the physical hardware is pushed to a state of constant kinetic stress. Bearings degrade, conveyor tracking drifts by fractions of a millimeter. Optical lenses collect a layer of industrial dust from thousands of tumbling cardboard boxes. We have engineered an environment where an automated facility operates under flawless mathematical logic, yet its entire operational stability remains completely vulnerable to the physical reality of a single piece of smudged ink. When the scan tunnel encounters the smudged barcode at 3:15 a.m., the automated system faces a logical crisis. The high-speed cameras scan the label, but the blurred ink corrupts the data string. Because the machine cannot guess or interpret, it executes the only fallback command it knows. It flags the item as an unreadable exception. Let's isolate the point of failure. In a system built on continuous movement, an exception is a sudden injection of friction. Instead of tilting down a standard outbound chute, the package is routed onto a secondary rejection lane. This lane bypasses the automation and leads directly to a manual correction station, a single physical table where a human operator must manually type in the tracking number. Under normal volume, a manual station handles these exceptions with minimal delay, but at peak hours, the margin for error does not exist. If a brief cluster of unreadable labels arrives in rapid succession, a physical bottleneck forms instantly. The rejection lane fills to its physical limits and packages begin backing up toward the primary crossbelt sorter. This triggers a cascade of digital safeguards. To prevent packages from colliding or falling off the tracks, automated optical sensors detect the pileup and instantly halt the preceding conveyor belts. Within moments, a failure at a single manual workstation ripples backward through the facility. The main intake line stops. The trucks at the loading docks cannot unload their cargo because the internal staging lines are completely full. Outside the facility, a line of logistics vehicles begins to form on the tarmac, idling their engines while the clock moves closer to the morning delivery deadline. The entire operational infrastructure is brought to a standstill, not by a catastrophic power failure or a software virus, but by the physical displacement of a few drops of ink. When a high-speed logistics hub halts, it uncovers a fundamental rule of engineering. Failure cascades exponentially, but recovery proceeds one intervention at a time. An automated network cascades into collapse in seconds. Resolving that collapse requires pulling the system out of automation and placing it directly into human hands. Here lies the operational paradox. We build automated infrastructure because machines move, sort, and process physical data at speeds no human workforce can match. But when an unreadable label corrupts the data string, the algorithm reaches its absolute cognitive limit. The machine cannot infer, it cannot guess, it cannot improvise. To resolve the exception, the system must hand the problem back to the one element it was designed to replace, the human operator. While the scan tunnel processes tens of thousands of packages an hour, a human operator at an exception desk must manually inspect the physical label, cross-reference damaged tracking numbers, and manually rekey the data one item at a time. The throughput collapses from automated scale to human scale. Because manual intervention operates at human velocity, the backlog does not clear when the problem is solved. It continues to build. Every minute spent manually clearing a jam adds compounding delay to the intake lines, the dock doors, and the delivery schedules waiting outside. This is why operational recovery is fundamentally slower than failure. Automation creates high-velocity efficiency, but it strips away resiliency. When an automated system breaks, it cannot fix itself, and the human safety net forced to catch it is constrained by the inescapable limits of human speed. The modern economy operates on digital expectations, but its recovery will always be governed by physical reality. Every investigation ends with a final verdict. The breakdown of a sorting hub isn't an argument against automation. It simply shows where its limits lie. To get maximum speed, we built logistics networks for perfect conditions. We cut out downtime, removed extra space, and pushed speed to the absolute limit. In doing so, we built a system that trades safety for speed. When a system is tuned so tight that a smudged barcode can freeze an entire region, the problem isn't the ink. The problem is the lack of margin. Real stability requires a basic trade-off. You cannot have maximum speed and maximum resilience without leaving room for recovery. Fast systems aren't fragile because they move quickly. They're fragile because they leave themselves no room to recover.